We're going to get started and continue with hypothesis testing. We got started with the one sample hypothesis test last week, and with some sort of general things about hypothesis testing. And we're going to move on to two sample tests tonight, where we're, instead of comparing one sample to a hypothesized population, we're comparing two samples and a null hypothesis of whether they seem to have come from the same population. So we'll cover that for both independent and so-called paired tests with the T and Z distribution, along with their assumptions and associated confidence intervals. So just to do a quick review of last week, wherein we covered one sample hypothesis tests, and the week before that confidence intervals. You'll recall that to construct a confidence interval from a sample, you use the sample mean, the standard deviation. If it is a known standard deviation, then we would use the Z distribution. And for a given confidence level like 0.05, we would use the critical value of that test statistic for 0.025, or for half of that. And this is the so-called margin of error that we go above and below the sample mean in order to construct our confidence interval. And then similarly for hypothesis tests, rather than constructing a confidence interval, we calculate a test statistic. So rather than using the critical value of the test statistic, we calculate an actual test statistic for a sample and compare that to the critical test statistic, such as the Z alpha over 2. And if this Z is larger than in absolute value than the critical value, then we reject the null hypothesis. And the basis of that is that we know what the distribution of this test statistic is if the null hypothesis is true. So if it's very improbable that what we observed came from that null sampling distribution, then we reject the null hypothesis. And that's a very general approach to hypothesis testing for all different tests that you will learn, that you make an assumption of a null hypothesis and you calculate a test statistic where you know what its distribution is under repeated sampling when the null hypothesis is true. And if it seems to be part of that distribution, you accept the null. If it does not, then you reject the null. So we then went into the T distribution. The only difference here is that the standard deviation is not known, but it is estimated from the sample. And that sampling distribution widens out a little bit in the tails because of the added uncertainty in the standard deviation. And both the confidence intervals and the hypothesis test remain the same, except that you use a T distribution instead of the Z distribution. And that T distribution has one more parameter in it, rather than just, well, there's only one standard normal distribution, but the T distribution has, there is a different one for each degrees of freedom. So you need to know how to calculate the number of degrees of freedom for the test that you're doing, and that tells you which T distribution you will use for your confidence interval or your hypothesis test. Now, the ideas when we move into two-sample hypothesis testing are pretty similar to one sample. What's really going to change is just how we calculate the test statistic. But all of the concepts about how you're doing it will remain the same. One difference or just one new conceptual thing that you'll have to think about is whether these two samples are independent or whether they are somehow paired. So independent samples would be two separate groups of people, like a case control study, for example. There's no relationship to them. They're both independent samples. A paired sample would be where there is some kind of a natural pairing between those two, such as if they were two sets from twin pairs. So if we had twin pairs that were selected where one of the twins had left their parents' home and the other one had stayed at home, and we were making that comparison. If it was the same subject before and after an intervention, all of these cases where you can think of some natural pairing between those two sets of observations, that is a so-called dependent or paired sample situation. And you need to recognize which, because the tests aren't interchangeable. You need to choose the correct test depending on whether the data are paired or not. Just a few examples of unpaired measurements. We're talking about the birth weight of unrelated boys and girls. Here the hypothesis, or the populations would be boys, one of the populations, and girls, the other population. Laboratory results from 2 different participants in a clinical trial. Those are unpaired, just two different people. Or say comparison of healthcare costs in the US versus Canada. These are all 2 independent samples coming from 2 hypothesized, potentially different populations. Lots of ways that measurements could be paired. So yes, the twins example, this is clearly paired. Pre-post measurements before and after some treatment on the same individual. We did measurements on the left and right eyes of the same individual. Some sort of measurements between twins or husband-wife pairs, or 2 different methods of making a measurement on the same specimen. So, 1 specimen, 2 different ways of making a measurement on it, and you're comparing whether they're the same. These are all examples of paired dependent measurements. Straightforward? Good. All right, which of these are paired measurements? Just to make sure. We've got average heights of males and females. It's easy. Unpaired. Anxiety levels of individuals before and after an intervention. Paired. It's paired, they're the same individuals. Anxiety levels of 2 groups, one with and one without the intervention. Unpaired, great. You've got it. So if there's no pairing, you can't use a paired test. You wouldn't even be able to. If there is a pairing, you could make the mistake of not using a paired test, but it would be an error. So paired tests are essentially the same as the 1 sample tests. So just to compare the z-test for 1 sample, the z-statistic was the sample mean minus the hypothesized mean under the null hypothesis. Sorry, this should be a sigma if it's a z-test. Let's see if I can... There. So in the paired sample case, the test statistic looks essentially the same, except that you calculate the differences between the pairs, and it is the mean difference instead of just the sample mean that goes into the test statistic. So you have all of these pairs of measurements. For each one, you just subtract. You get a new 1 sample data set and continue like it is a 1 sample test. It's the same.
So D is the difference between the 2 means?
Yeah.
Paired symbols, and then that other symbol is...
Which other symbol?
That's the O with the fuse on top. There, that's not sigma. Is it on the paired sample? Z equals D minus...
This is sigma. Let's call this sigma.
On the bottom is sigma. But then on the numerator, right? What's D minus delta? Is that?
That's the difference under the null hypothesis.
Okay.
So under the single sample, this was the mean, the hypothesized mean under the null hypothesis, and here it is the difference under the null hypothesis. Yeah, that's a delta, and this, I'll call this a sigma underscore d, the standard deviation of the differences. So yes, the delta 0 is the population mean difference under the null hypothesis. And usually that would be 0, so this would just be d bar. Usually your null hypothesis is no difference. So in constructing a confidence interval, it is the same thing. The x bar, the mean of your sample, gets replaced with a d bar, the mean of your differences. And the s here is calculated from the differences. So it's exactly the same, except you're working with differences instead of just the values themselves. Okay, so far the only thing you have to remember is if you have paired data, you're comparing these pairs, you have to use that pairing, calculate those differences, and continue as if it were a one sample test. No problem. So let's compare the two in the cell phone study, where the question was, does cell phone use while driving impair reaction times? And in this, so this is an experiment where you have your participants use a machine that simulates driving situations, and then you flash a red or green light, and you have to press a brake button as soon as you see it, and your reaction time is measured. So in our first experimental design here, 32 students are randomly assigned to the cell phone group and 32 to the control group that are not using a cell phone. So is this a paired design or an independent samples design?
Unpaired.
Unpaired.
It's like the anxiety group. If you had anxiety where you have one group receiving intervention and one not. It's like randomly assigned.
Yeah.
It's not the same group experiencing.
That's right. It's not the same group. Everyone is randomly assigned to one or the other. So there's no, it's not paired in this design. So here is our imaginary data. In the control group, we have a median of about 530 milliseconds, and in the cell phone group, it's a little higher, maybe 580 milliseconds with one outlier. So yeah, the means 533 and 585, with N1 and N2 both equal to 32. So how do we calculate the t-statistic in this case? We've got two groups, treatment and control. We've got potentially two different population means, but under the null hypothesis, those two means, the mean in the control group and the mean in the treatment group, are equal. So it is the difference in the means that our hypothesis is on, not a difference in individuals. So how do we do that hypothesis test on a difference in two means? Well, it's still fairly similar. It's not quite as straightforward as in the paired case. In this case, we calculate here that the difference in the two means minus the hypothesis difference, which will be 0 in most cases, and in this case. But then we need this pooled standard deviation. And we can just calculate that as a as essentially a weighted average, just calculating the each variance divided by the sample size of that group, adding them up, and calculating a square root. So with this alteration, so whether this is sigmas calculated from the population or s's from the sample, the only difference from the one sample case is this difference in how we calculate a pooled standard deviation. So here, that was the z statistic. With the t statistic, it's the same thing, just using the s's. All right, so the t statistic and the z statistic look almost the same as in the one sample case, just with this special formula for calculating the standard error. Instead of before, it was just the standard deviation divided by the square root of n. In this case, it's this weighted thing that brings in both the sample sizes and the standard deviations of the two groups. So it's not too much harder. It's a little bit harder. So actually, those were not pooling the standard errors. You can pool the standard errors as well, and this is an option that you will find in your test, whether or not you want to pool those standard deviations, and there can be reasons for doing it either way. But the equation is a little bit more complicated when you pool them. But again, it's just an alternative equation for calculating the standard error with using the two standard deviations and the two sample sizes of your two groups.
So which one are we supposed to do?
It's a good question. And I'll talk about that a little more, but which should you do? Should you pool the standard errors or should you not pool them?
When you say pool them, so that would mean, because I thought we're looking at the difference, we're not looking at the difference of standard errors.
We're looking at the difference in means, of the right. treatments in the control group. So I don't know, you tell me, do you think that that the variability, that the treatment, the cell phone usage might also increase the variability in response times, or just the mean?
It's a good question. I don't know. I have no idea. I would think it could, because, right, if you're expecting to see some kind of effect, or I would say if you're expecting to see some kind of effect as a result of using cell phones, then you might expect that, then seeing greater variability would kind of suggest that you are seeing some kind of effect, right? Because it's causing variance. Some people are being affected by the cell phone use,
I think it's reasonable in this case to think that the cell phone usage might not only change the response time, it might also change people's response times differently. Maybe some people tend to get more engrossed in cell phones than others. So, I think it's something to think about. And if your sample size is very small, then you have very little evidence from your data to tell you whether the standard deviations look the same for the two or not. With n equals 32 in each group, that's a pretty big sample, and you can estimate the standard deviation pretty well in each of those groups. So in this case, we have a fairly large sample size, so we can get a good estimate of the mean, or of the standard deviation from each sample. And we have, I think, we can reasonably expect that maybe the treatment does affect variability. So I think in this case, you should use the unpooled variances, allow for the variance to be different in the two groups.
That's the top. Is that the top? It's not the equation shown here.
Right. This one is pooling. This is without pooling. And in your software, the one without pooling is also called a Walsh t-test. And it has, so yeah, you'll get to choose when you do the t-test, either by hand or with software, but you should be aware of what you're using and make a decision. So a bit more on pooling the standard deviation. The test tends to be more powerful. If the standard deviations are pooled, you're estimating fewer things, so you have more degrees of freedom. But if you're wrong, you might actually increase your type 1 error rate. If the means or if the standard deviations are different and you pool them anyways, it is not necessarily a safe thing to do. So if you're unsure, then not pooling is safer. There are cases, however, where not pooling is not necessarily safe. If you have one very small group, like say only 3 samples or something in a group, estimating the standard deviation from that is there is a lot of error involved in doing that. So with very small sample sizes, there can be advantages to pooling. But here's a rule of thumb, just, I don't know, something maybe to think about. If your 2 estimates differ by more than a factor of 2, then that's pretty good evidence that you shouldn't pool. You know, that said, if your sample size is only 3 in each group, it could vary that much just by sampling. And another rule of thumb to override the previous, if either of your sample sizes are less than 5, this is what I mentioned, that if you have very small samples, it's difficult to estimate the standard deviation, and it's better to pool the standard deviations. The degrees of freedom is simple when you're pooling. It's just your total sample size minus 2. But if you're not pooling, the so-called Walsh t-test, and I should write this down here. It's the Walsh t-test. Then your degrees of freedom is non-integer, and it's given by this complicated formula. But you can estimate it conservatively just by taking the minimum of your 2 sample sizes minus 1. So if you're doing it by hand, this is not a bad, just quick way to do it, and it will not make your p-value smaller than it should be. By conservative, I mean that if anything, it's going to increase your p-value. So the only time it will matter is if your correct p-value is 0.49 and it brings it up to 0.049 and it brings it up to 0.051, something like that. But most of the time we're going to use software to do the t-test, and it will use this exact calculation of the degrees of freedom for the Walsh t-test. Let's go through these steps for the cell phone study. The 5 steps that we covered. Step 1, we'll choose a type 1 error rate of 0.05. Step 2, write out the null hypothesis that the mean reaction times of the control group minus the mean of the treatment group in the population is equal to 0. The alternative hypothesis being that it is not equal to 0. So even though we think that probably, if anything, cell phone reaction should increase reaction time, it's still a 2-sided hypothesis test. Calculate our test statistic, and based on those means and standard deviations, I'm going to skip through the gory details, but if you want to use this to test through, you get a t-statistic of 2.628, and In the pooled case anyways, our degrees of freedom is 30 plus, let's see, did I get this right? Why did I put DF equals 56 here? Maybe this is the unpooled case in the, no. I feel like it should be DF equals 58 here. So yes, I'm not sure why I wrote 56 there, but since there were 30 in each group, the number of degrees of freedom, 30 plus 30 minus 2 is 58. I'll double check that. And that gives it, either way, this is going to have very little difference on this p-value of 0.011. Either way, we're going to reject the null hypothesis. And then finally, putting it in the language of the problem at hand, we conclude that the mean response time of the self-limiting users group is significantly different than the control group, and it is greater. So we could take these data and conclude that cell phone usage seems to have a distracting effect on response time. So that was an independent sample design. What would be a reason for doing an alternative design with a paired or dependent design? So where we use the same subjects for both groups. We have each individual do the simulations twice, once while using a cell phone and once while not using the cell phone. What would be a reason for designing the study that way? Yep.
Takes out like the individual differences that could affect reaction times. You're only comparing the cell phone.
Yeah, exactly. It takes out the individual variability in reaction time. So you're going to have some people who have very quick reactions. Generally, they're faster when they're not using cell phones, and they're probably faster when they are. And you take out that element of individual variability and just compare directly within an individual the effect of cell phones, which is what we're interested in. So what practical advantages would that have for a study?
Less people to track and make sure that they complete the study. It's less expensive. You have to, well,
yeah, so either it could be you need to recruit fewer people to your study, so it's less expensive, or it could be making better use of the same number of people, so you have better power to say whether the difference is statistically significant given the same number of people. So if we had the resources to recruit 60 people, we might still use 60 people, but test them each twice instead of once. I can think of a potential risk of the paired design that you would have to be careful for and plan for in your experimental design.
Bias?
What kind of bias?
Participant bias.
What do you mean?
Like, you know, they kind of figure out what you're driving at, no pun intended. And so they'll be worse when they're using a cell phone or whatever, or maybe they'll be better because they'll be trying to guard against it.
Okay.
Normally,
okay. So yeah, maybe there could be bias towards the participants' desired outcome of the study. Then in that case, that's possible. What else? What if the participants aren't biased?
say maybe age. If all of your participants are like 85.
Uh-huh.
Something that would impact like their cognitive or like reaction time.
Mm-hmm. Well, so in the unpaired case, we would control for something like age through randomization and maybe stratification as well, by ensuring that the age distribution in the randomized control and the treatment groups are the same. In the paired case, I don't see age as being like a confounding factor because each individual is their own control. So I don't think that's an issue. But there is another issue that is, I think, an important one here that no one has thought of. So I recruit all of my participants and have them take the driving test twice, once while using a cell phone, once without.
Practice effect.
Practice effect. So yes, practice effect, you have them take this, maybe the same course twice, maybe the second time they know what's coming. And so their reaction time is better. Or maybe okay, what if we use different courses? So we try to get rid of the practice effect. Then what? Is there still an issue?
It would have to be exactly identical or somehow. Otherwise, you can't really compare the first and the second test.
It would have to be comparable enough. Okay, let's take the practice effect. Let's suppose we know that there is a practice effect, or and that it causes people's reaction times to decrease. How could you control that in your experimental design? So what's going to happen if we have everyone use their cell phones the first time they take the test and no cell phone the second time they take the test?
Would they maybe do better with their cell phones relative to how they would do without if they use their cell phones first?
Yeah, maybe. Or maybe the other way, maybe they get tired after they take it once and they're more bored and paying less attention the second time. But the point is that in that case where we have them take the test first with a cell phone and second without, the order in which they're taking the test is completely confounded with the treatment. And so you can't separate the effects of test order and treatment. So if we think of that in advance, we can control it. We can say, okay, randomly half of the people will use the cell phone first and the other half will use it second. And then it's no longer confounded with treatment. We can estimate both the effective test order and the effect of cell phone usage separately.
Would you test to figure out what order works better as far as getting a result, and then do another experiment using that order? Or could you accomplish both goals in the same experiment?
I mean, you might do a pilot study where you're just kind of figuring out your driving test and such, and maybe you would test it on a few people to see if there is a big practice effect or fatigue effect, and maybe try to fix that. But as long as you randomize the test taking order so that it's not confounded with the treatment, then you can estimate it in the design. I mean, if there's a huge practice effect that is much larger than any treatment effect, then you might have a problem even with the randomization. But if that effect is not huge, then it should be fine if there's some practice effect or fatigue effect. But the lesson of that story is that when you do experiments, if you have some artifact of the experiment that is confounded with your treatment, then after you collect your data, there's going to be nothing you can do about it. And this comes up a lot in real life studies, confounding of interviewers. So you have two different study groups. You have one interviewer interview this group and another one interview the other group. Then your interviewer effect is confounded with your study groups, and there's no way to disentangle those two effects. One is an artifact and the other one is the thing that you're actually studying. So this is a kind of a general lesson in experimental design. You need to think about any possible sources of of bias or artifacts in your experiment, and there always are some, and then they need to be randomized or stratified to remove confounding between experimental aspects and your treatment or your whatever you're studying.
This might seem, I don't know, it seems like a silly question, but is there a standardized list that like all researchers go to when designing an experiment to see what sorts of treatment groups or whatever they're doing an experiment on like fits into what category and what biases might be present within that category? Is there like a common resource that is used by kind of universally?
Not that I know, but it's a good idea because there should be.
Yeah. That seems like a lot for like one person or even a team of people to think of, because there's always, I mean, some like problems with replication and things like that.
They have like a cheat sheet or something.
Yeah.
Yeah, they do.
A cheat sheet. I mean, it would be pretty context specific.
Yeah.
Like,
Because when I was in residency in family medicine, we had like what kind of bias with what kind of test, something like this.
Would you send it to me?
No, I don't have it.
Oh, you don't have it.
This was like a long time ago. Like,
Yeah. I mean, I've never seen that. Even though, like, for, you know, in my field, genomics, some of the sources of artifacts are so common that they should really be controlled for in every single experiment that everyone does, and yet they aren't.
So I'm just like, so there's no like protocol for designing protocols. I mean, it's just, I don't know.
Yeah. I mean, once you, well, okay, there is maybe one thing that is a general, not a protocol for designing protocols, but a general protocol that extends the double-blind method to laboratory methods. So, you know, double-blind method is where if you're doing a clinical trial, then the patient does not know whether they're receiving treatment or control, and the doctor does not know whether it is treatment or control. That's the double blinding. There is an equivalent of double blinding in laboratory tests as well. And the way that happens is someone like me, the biostatistician, does the randomization of samples. So we have 60 specimens that need to have a test done on them. I randomize the order and provide them to Tony, who's in the environmental lab or wherever that they're going to do the testing, and that person doing the testing has no idea which are the treatments and which are the controls. So it's like a double-blind method, because there can be a lot of different sources of bias coming up in the lab. Like, you know, they recalibrate a machine, they do some today, some tomorrow. There's some reagents, and you run out of a bottle and start opening a new bottle. All sorts of things that are really hard to you know. It's hard to think of all of them, but if you have that double-blind randomization, it at least guarantees that if you run out of your chemical and open a new bottle, you're not going to be doing all of your controls on the new bottle when you did all of your treatments on the first bottle, because they're randomized between the two. But it is kind of a common thing in experimental design to try to sit down and think about what are your confounding factors, because you can do better than like that. Complete randomization is, you know, it's very helpful and it prevents bias, but if you have known confounding factors, you can actually do better through so-called blocking, where you know, if you have old and young participants, rather than just randomly assigning everyone to treatment and control, you guarantee the same balance of ages in the two. So you go in your old group and assign them randomly to treatment and control, then go in your young group and assign them to treatment and control. So it's a little bit more active than just complete randomization. Okay, so now we have these, we have 32 students. Each of them has a yes or no using cell phone. We calculate the differences and do the test on those differences, a one sample test. And so we get that column of differences and then use the Z or T methods for one sample. All of this is the same. There are 5 steps of hypothesis testing. I did add a step 0 here, which wasn't in the other ones, which is choose an appropriate test and assess the assumptions, just because we chose the independent samples test and now we're choosing the dependent or paired samples test. So, and we do that before going on to step 1 of choosing our alpha.
It's almost always going to be like a test of this thing.
Yep.
So you have like census population for 2 countries or something like that.
Anytime you're doing inference, you're doing a hypothesis test, there's going to be a test statistic involved. If you're talking about populations, then and you have all of the data from 2 populations, then you don't need to do any inference. You have all of the information. So you would just then say, okay, how much is the difference between the reaction times, for example? If we went out and tested the impact of cell phone usage on reaction times on everyone in the population, you wouldn't need to do inference. You could just say, here's how it changes response time.
I was thinking of just instead of the t-test, you just assume a normal distribution. If you either know the population standard deviation, right, or your sample size is large enough. Those are the 2 criteria for t versus normal distribution.
Sorry, what's your question now?
For using the t distribution instead of like the regular z-scored normal distribution.
It's just whether you're estimating the standard deviation from the sample or not. So if you estimate standard deviation from the sample, then it is a t distribution. And as sample size gets very large, then the t distribution is very similar to the normal distribution, and it doesn't make much difference. But it is always different. And you notice that difference more the smaller alpha is. So if alpha is 0.05, then if n is 50, you probably get almost the same. You're going to make the same decision. But the further you get out on the tails, like if you're using an alpha of 0.001, then those differences in the t distribution and the normal distribution will persist for larger sample sizes. If for some reason you're doing an alpha of 10 to the minus 6, then you'll see a difference in those p-values even up to n equals 500. It's out in the tails, and the larger the sample size, the further out in the tails you have to go to see the difference between the z and the t distributions.
So you should use as a rule of thumb, you should use the t distribution unless you know the population standard deviation. Yeah,
if you come into the test already having sigma, you're not estimating it from your sample, then you use the z distribution. But if you estimate standard deviation from your sample, then it's a t-test. Yeah. All right, so getting to the end here, the number of degrees of freedom was 32 participants minus 1, 31. At t statistic of 5.46, and we reject H0, and we can also build a 95% confidence interval on the difference. So we're not using 2 different confidence intervals here. We're constructing a single confidence interval on the difference, and that is comparable to the hypothesis test. If that confidence interval includes 0, then you don't reject the null hypothesis. If it does not include 0, then you would reject the null hypothesis, and those 2 are equivalent as long as you construct the confidence interval on the differences. using the methods you've learned today. So in the paired test, if you're doing box plots, you would probably draw just a single box plot on the differences. Let's do something more fun though. Let's look at paired and unpaired tests for, I'm testing a null hypothesis here that Tony and I look the same age. So I took all of these guesses, all of your guesses, and tested a null hypothesis that the average guesses for Tony's age were the same as the average guesses for my age. Now, is this paired or unpaired? It is paired because it's the same person making two guesses, so they're not exactly independent guesses. It is unclear though as to whether there is any tendency for someone to overall guess higher ages or lower ages. There probably is, and that if we had like a 10-year-old in here, they're probably going to guess we're really, really old or have no idea how to guess. Whereas if they're people about our same ages, maybe they would notice the true differences a little bit more. But probably there is some relationship between someone's guess for Tony's age and for my age. But I did it both ways. In the first one here, this is the paired test, the one that's probably correct. And so I just took the difference and did the one sample t-test. You see that the difference, the mean of the differences in age guesses is 19 years. And if you look over on the unpaired, it gives two different estimates, the mean estimates for each of us. And if you take this difference, you'll find it's exactly 19.26087 years. So the difference in means is the same. It's just that the t-statistic is different because of the way the denominators are calculated, and the p-values are different. So in the one sample test, we got a p-value of 10 to the minus 12, and in the two sample case, a p-value of also about 10 to the minus 12. So it didn't make a big difference. It seems like there isn't that much of a correlation between people's guesses for the two of us. They're making more or less independent age guesses for the two of us. So 95% confidence interval on the difference in our ages is between 16 and 22 years. I'm not sure how accurate that is.
67 and
43. So 23 years is?
Yeah,
They think there's, we look more similar in age. Okay, let's do another hypothesis test. This is one because I have data from last year as well. I took the data from last year's class and took all of their point estimate guesses for my age and compared them to your guesses of my age and plotted them. And my null hypothesis here is that I'm immortal and I'm not aging. And so the population mean of age guesses for me would be the same last year as it was this year. I don't know. There does seem to be some increase though in the median guess here, which worries me. But I'm going ahead and doing this t-test for the 2015 and the 2016 data. And in R, you specify this var dot equals true to say that I want to pool the variances, something different in SPSS. But let's see, the p-value here is t-statistic of minus 1.22 and a p-value of 0.22. So there's not enough evidence to reject the null hypothesis that I'm immortal. So now, does that prove that I'm immortal?
told us.
Come on, yes or no?
No.
No, it doesn't prove I'm immortal, and that's actually a good example of, as they say, that no evidence of a different no evidence of a difference is not evidence of no difference. So just because we don't have a super large sample size here, and just because we can't show, there isn't evidence that the mean of the age guesses for last year and this year are different. It doesn't prove that there is no difference, only that we don't have enough evidence to reject the null hypothesis of immortality, unfortunately. And in fact, the mean guesses increased from 38.8 to 40.6. So in fact, the average guess did increase by more than a year. So, so that is consistent with aging, but it's with not a large sample size, only 37 degrees of freedom. All right, so to summarize these two sample procedures, with paired samples, if we have continuous data, you take the differences and then use the one sample version. This gets a little bit complicated for proportions, and we're not going to cover it. You actually, this is easiest to do with a logistic regression or generalized linear models when you're dealing with proportions. But for independent samples, we covered today how you take the differences between the means, and we have these slight modifications for estimating the standard error for the Z and T test. And you can also do this with proportions, taking the differences between those two proportions, but you only use the one sample Z test methods. So, as I mentioned, I've shown you how to use how to calculate the confidence intervals, and as before with the one sample tests, there is an equivalence between hypothesis testing and confidence intervals, which you can use by checking whether or not zero or the difference hypothesized under the null hypothesis falls within your confidence interval. But the important thing to note here is that we construct a single confidence interval on that difference. We don't calculate a confidence interval for each individual sample and look for overlap. It's just one confidence interval. That's a common misperception that people will do because it's easy to calculate a confidence interval for a single sample. They do it for the two independent samples and say, oh, there's overlap, so I'm not going to reject the null hypothesis. But it doesn't work that way. There are plenty of situations where there are overlaps in the two confidence intervals, but still you reject each zero. There's only equivalence when you calculate a single confidence interval on the difference in the means. Got that? Okay. So, just to summarize the assumptions, for the unpaired example, we have to make the assumption that the tests are independent. And for the paired, the assumption that these pairs are the unit, but that those units are independent. So in the cell phone example, each individual in the study is an independent, their test is done independently of each other, and there isn't a relationship between the individuals in the study. The assumption is that the population values, or the differences in the paired case, are normally distributed. That is the case for both t-tests and z-tests. So the population is normally distributed, and that our data are obtained by a random sample from the population. So remember those assumptions. And just to make it graphically, that the caveat that I gave about the equivalence between the two sample confidence interval and the hypothesis test, this is the correct way to do it. Give it a nice hockey stick there, and this is the incorrect way to do it, in case you get tempted to try it this way. Any questions about this? Is that clear why I'm saying one is correct and the other is incorrect?
So just like if you were to give an example with numbers for those two.
Yeah.
Like let's say X1 95% confidence interval, like on the bottom of like the mean of 1 is like say whatever 20, and then all the way on the right for X2 it's like 80. So you would make it between 20 and 80 would be your confidence intervals. Your 95% confidence interval.
Okay.
Is that correct?
So if our difference in means were 50 and the margin of error were 30, then the confidence interval would be between 20 and 80 on the difference in means. And because that 20 to 80 does not include 0, which is probably our null hypothesis, you could reject the null hypothesis. And that's fine because we calculated a confidence interval on the difference in the means of the two samples.
It'll be clearer to me with like I guess in lab or whatever kind of homework we do. So like what I'm just trying to picture the way. Yeah.
The key thing is that whether you're dealing with one sample or two samples, you're going to just be dealing with one confidence interval. So in the two sample case, it's one confidence interval around the difference in means of those two samples, or around the difference in means of the two populations.
Which is based on which the equation we saw takes into account, right?
Right. Takes into account the variance in each of the samples. Yep. Okay, I'm going to wrap up just with some more general discussion about limits and interpretation of hypothesis tests, because there certainly are some. So, number one, statistical significance is not the same as practical significance. So, you know, the statistical significance, the p-value, what we've learned is that it controls type 1 error rate, and it is the probability of observing something like our sample, or even more extreme if the null hypothesis is true. But if the sample size is very small, then even large differences might not be statistically significant. And conversely, if you have a very, very large sample size, then tiny, tiny differences in means can be highly statistically significant. And one example I saw of this was this analysis of eBay camera sales and the effect of minimum bid on the eventual sales price. So this was an analysis of 341,000 sales, and it found a coefficient of 0.1, a p-value that was essentially 0, with the interpretation that a 1% increase in the minimum bid is associated with an average of 0.09% increase in the final price, all else constant. So whether that is practically significant or not, I don't know. It's highly significant statistically. It didn't just occur through sampling, because you don't see a lot of variation in average prices or average anything else with this large of a sample size. But just keep in mind that a tiny p-value for a large sample size doesn't necessarily mean that the difference you see is clinically important or practically important for, you know, doing a public health intervention or anything else. It just means that it's not due to random sampling. the p-value is not interpretable as the probability that the null hypothesis is true. So you do your p-value, you get a value of 0.01. That does not mean that there's only a 1% chance that the null hypothesis is true. And similarly, p-value of 0.99 does not mean that there's a 99% chance that the null hypothesis is true. It doesn't tell us anything about the probability that the null hypothesis is true. It tells us about the probability of observing our sample if the null hypothesis is true. Right? So the worst abuse of this would be to say that to use that p-value as evidence in favor of the null hypothesis. But that's just not the interpretation of the p-value. What is evidence for the null hypothesis is the power. So if you do your power estimation and find that you have 90% chance power to detect a difference and you still don't detect a difference, that tells you something about the probability that your null hypothesis is actually true. Just by way of an example, researchers did not find evidence of any effect of treatment on self-reported pain, p-value of 0.2. Does this mean that there is an 80% chance the pain reliever has no effect? No, it doesn't mean anything like that. It just means we haven't found evidence of an effect. Number 3, so although alpha equals 0.05 is super common, used almost everywhere, it isn't a magical value. So if you have a study that has 2 primary endpoints, like we have that school study that had several different endpoints around anemia and educational outcomes, if they have similar p-values, one is 0.04, the other is 0.055, that doesn't mean that for one of them there is an effect, and for the other one there is not an effect. It means it's marginal evidence at the 0.05 level in both cases, and in fact, there's very little difference between those two p-values. You should think of the p-value as a random variable, even given exactly the same conditions and exactly the same populations. If you take another sample, you're going to get a different p-value because it is a random variable. So, we choose alpha equals 0.05 to limit the probability of a type 1 error, and if it doesn't meet that threshold, then we can't rule out the null hypothesis with the same confidence with that 5% of a type 1 error if the p-value doesn't fall within there. But it doesn't mean that we haven't seen some evidence in favor of our alternative hypothesis. This is a bad one. Forgetting that significance tests are about the central tendency of the population and they're not about individuals. This is one that I'm sorry to say, horribly tripped up students on exams before with questions getting at this. So here's an example of what I mean. Researchers measure serum lead levels in a random sample of 100 children in an area with potential lead contamination. They find that the mean serum level is 5 micrograms per deciliter, which is less than the normal limit of 10 micrograms per deciliter. And they reject the null hypothesis that mu is equal to 10 micrograms per deciliter with a p-value of 0.01. Does that mean that fewer than 1% of children have serum levels exceeding the limit? No. What does it tell you about the fraction of children with serum levels exceeding the limit. It doesn't really tell you anything about the fraction of individuals below the limit. Like, it tells you that, that our sample is inconsistent with a mean of 10 micrograms per deciliter. Yeah.
Could you say that it shows that there's less than a 1% chance that that difference is due to random error?
There's less than a 1% chance that the difference in means that we observe is due to random sampling.
And is that the correct way to report that number? If you were to, like, you were given those numbers and you had to write a sentence.
You could say that the mean lead contamination was less than the normal limit of 10 micrograms per deciliter, a difference that is statistically significant, and then put in brackets, one sample t-test, t equals this, degrees of freedom equals this, p equals this. Yeah, I mean, it probably means that more than half of the children are something less than the limit. But if you had a large sample size, you could imagine that even if you had a mean of 9.9 micrograms per deciliter, you might still reject that null hypothesis with a small p-value, even though almost half of the children exceeded the limit. So it's just about that central tendency, the mean. It's not any protection. So this test does not provide any protection against individuals exceeding the limit. So it's probably not even a very appropriate test to be using in this case if you don't want anyone to have blood levels above this safe limit. So number 5, assuming that because n is small, you just can't believe any results of a significance test, or the converse of that because n is large, the results must be true. And that's problematic because statistical tests are designed to account for sample size as long as the assumptions hold true. So as long as we have a probability sample and we know the probabilities of sampling of each individual in the population. So for the purposes of inference, a small sample with a representative random sample is going to be better for inference than a large sample, but the one that is biased or where it's not a probability sample. And you remember through all of this, we haven't talked about the size of the population, only the size of the sample. So whether the population is 1 million or 100 million, doesn't matter so much as long as we actually have a representative random sample from that population. It of course gets more difficult to take a random sample of a larger population, but it still holds that if you have a random sample, it's the size of the sample that matters, not the size of the population. And the degrees of freedom in these tests account for the variability in the sampling distribution due to sample size. And you should be skeptical. Study design is critical. And we talked about this a little bit with the cell phone study, that basic flaws in producing the data, such as voluntary response samples of convenience, or not properly controlled experiments, such as if we had test taking order confounded with treatment. All of these things can introduce bias, and they're not part of the p-value calculation. The p-value controls only for random sampling error. That's it. So if any of these other sources, can also produce type 1 errors, but they are type 1 errors caused by other reasons, not random sampling. And I say they're still a type 1 error just because they might cause you to reject the null hypothesis when the null hypothesis is true. And there have been some high-profile cases of this in my field and in other fields where null hypotheses were rejected due to biases in the experimental design. Keep in mind, tests can be statistically significant by chance. That's by design. We have incomplete information. The whole point is just that we have an idea of what our probability of making a type 1 error is. So it's a nice XKCD cartoon where they test whether jelly beans cause acne, and repeat this for all of the different colors of jelly beans until they find that green jelly beans cause acne with a p-value of less than 0.05. That's called multiple hypothesis testing, and that's more than just achieving statistical significance by chance. That's by statistical significance by uncontrolled multiple hypothesis testing.
If you have like a large enough data set and like a bunch of different variables, can't you just fish until you find something that's
For sure.
Yeah.
If you have a large enough data set, or if you have enough variables, you have 20 different colors of jelly beans, you can go fishing until you find something statistically significant. So something to be careful about and to be skeptical about. And that can happen even without any intent on the researchers. There's the so-called file drawer effect, where by researchers who do studies and don't get a significant p-value, don't publish their studies, they don't bother, and then other groups that find a significant p-value publish. And that's actually something that you can uncover in a meta-analysis. You can find evidence for that file drawer effect. But yeah, very, very common. There is evidence that in general, the effectiveness of drugs tends to be greater when it's first reported than in later studies. Because of those early studies, they tend to be small sample size. You need a big difference to get a significant p-value. And then as studies get larger and more of them are done, you see that effectiveness decrease more towards what it really is. Due to publication bias, getting ahead of myself here. But this has happened in some well-documented cases like this so-called robexetine. Passes effective for treatment of depression in 2001 in Europe and the UK, and it was later found to be both more harmful and less effective than originally reported due to publication bias in the original trials, and that the other small trials that had worse results just weren't published. And this is why the Food and Drug Administration and some journals now require trial registration. At least if it is for a human drug, they require that you register your trial in advance. So if you do 20 trials, they will know about it. Or if you don't, they won't publish or accept the results of your trial because you didn't register it before doing the trial. But for all sorts of other things, if it is not a human drug, then that trial registration is probably not required, and you don't have any protection against this kind of publication